Hello everyone, this is Dr. Young, and in this video we are going to talk about how to write molecular, sometimes called complete, molecular equations, ionic equations, and net ionic equations. It can be the same reaction, but there's different ways you can see them presented. So let's talk about what that looks like. This is going to be for our aqueous reactions, right, which are, again, where we just have water as a solvent. The main context that you're going to see this in is for precipitation reactions and acid-base reactions. Those are probably going to be the most common ones, the most common reaction types that you're going to see the molecular versus ionic versus net ionic equations be used. And I have here at the beginning just showing you what they look like, and we'll go into each one of them in detail. But these are the three different ways that you could write the equation, right? The molecular, which is probably the one that looks real familiar to you. That's where you write out all this stuff. The ionic equation is just a ton of ions, and it's really long. And then the net ionic equation is a real short one, real simple, real short one. So we're going to talk about why we'd use one versus the other one. And I'll say this now, but I'll mention it again. The molecular reaction is, the molecular equation is just kind of how we talk about the chemicals. Hydrobromic acid, potassium hydroxide makes water, and potassium bromide. The ionic equation is probably the most accurate in terms of what's actually dissolved in the water. So right at the beginning, that's all dissolved in the water. And then at the end, that's what's in the water. So it shows you all of the things that are actually there. Versus the net ionic equation just shows you the things that reacted. So realistically, in this equation, it's really just an H plus found in OH minus, a hydroxide, to make water. That's really all that happened. And these equations here, these are all the same equation. All three of these are for the same transformation, the same chemical reaction. So let's look at each of these in a little more detail. Now, the molecular reaction, which I said is also just called the complete reaction, it's called the molecular reaction, right? Because you just leave everything as, you leave everything together. You leave all the molecules together, etc. So there tend to be lots of molecules. Not even necessarily lots, but there tend to be molecules in this, which is why it's called molecular. You're not going to break up any molecules like the strong acids, for example. You leave them together. You're not going to break them up, and so they stay molecules. And it's also called the complete equation because, again, it's just kind of everything is there, and everything is exactly how you say it. So it's pretty straightforward. You just write the equation like you'd expect. Leave all the compounds together. You don't break anything apart. So like here's the example of that first one I showed you on the previous slide. Hydrobromic acid, potassium hydroxide makes water, and potassium bromide. You just leave them all together. You put the aqueous, liquid, aqueous for the different species, depending on what they are. Again, we're in water, so aqueous would be appropriate for these. And then here's another reaction. Sodium chloride and silver 1 nitrate make sodium nitrate and silver 1 chloride. Sorry, I said silver 1 chloride over here. Silver 1 nitrate makes sodium nitrate and silver 1 chloride. And again, you just leave everything together. So this is how we've been writing reactions so far. When we've been balancing them, all that sort of stuff, this is how we've been doing them. This is what we use for stoichiometry. This is the most common way to represent an equation. Now, then you have the ionic equation, right? And the ionic, just like the name suggests here, you're going to have lots of ions. Anything you can break into an ion, you're going to break into an ion. This is the longest way to write some of the reactions. As you probably saw in that previous slide, it makes things much longer. And the idea here is that you're going to want to break up, let me do this in a different color. So you're going to want to break up all the water-soluble ionic compounds and all the strong acids into their ions. You're going to leave all of the other compounds alone. You're not going to change them. So you don't change covalent compounds. Leave them alone. Right? So those things that have a small difference in electronegativity or no difference. You're going to leave covalent compounds alone. You're going to leave the insoluble ionic compounds. And you're going to leave the weak acids alone. You're going to leave them how they are. You're not going to change them at all. And if you're wondering, well, how do I know if it's soluble or insoluble, right? Remember, go back to those solubility rules. That's what we're going to use, right? Things that have alkali metals or ammonium tend to be water soluble. Things that have nitrate or acetate anions tend to be soluble. And then the lead, silver, and mercury compounds tend not to be soluble. And so I'm going to go through this and make all these decisions here, right? So And then as far as strong acids go, again, in previous videos, I know that HBr is a strong acid. All right, this is a strong acid. So I'm going to break it up into its ions. The H plus is going to be dissolved in water, and the Br minus is going to be broken up in water, right? Because remember, strong acids completely dissociate. That's their definition, right? They completely dissociate. There's 100% dissociation. And then I look at my KOH. I see that that's a water-soluble compound, right? I know it's water-soluble because it has potassium in it. So since I know this is soluble, I break it up into its ions also. So I have K plus dissolved in water, and I have hydroxides dissolved in water. So I've broken up all of those because both of those species, the HBr and the KOH, were water soluble. They break up in water. I have to draw the ions. Now I go to the second part here. Now I have water, but water is just a covalent compound. So I'm not going to break up water. I'm going to leave water alone. I'm just going to leave it. It's not an ionic compound. It's not a strong acid. I'm just going to leave it alone. And then I look at the last thing here, and I see I have KBr. Again, it has the potassium in it, so I know it's water soluble, so I break that up to K plus and Br minus. So that would make my whole ionic equation. If I wanted to convert this into the ionic equation, that's this whole thing right here. Apparently, everything breaks up into its ions except for water, because water is the only molecule there. That's the idea. And I could do that with the second one also, right? Same process. So I'm going to go look at my sodium chloride plus silver 1 nitrate goes to sodium nitrate and silver chloride, silver 1 chloride. Same ideas here. Looking at them, do I break it up or not? I have sodium chloride. Sodium's an alkali metal, so I know this is soluble. So I have Na plus and Cl minus. And then I look at silver nitrates, my silver nitrate. I know that things with nitrate in them are also soluble. So I say silver 1. And again, these are just the solubility rules we talked about, right, in a previous video. So that's all of those. That's done. And then I have sodium nitrate, which both of those make something soluble. So that's definitely soluble. So I write my Na plus here. And I've got my nitrate. And then I look at my silver chloride, and remember that silver makes it insoluble. So I do not break it up. So I just say silver chloride solid. I just leave it as it is. So that would be my ionic equation for this one. Right? So you break up all the water-soluble ionic compounds and these strong acids into their ions. Leave everything else alone, right? So that's what I did. I only had one strong acid in these two examples. That was the purple stuff, the HBr. The green stuff was all the water-soluble stuff, and the red stuff were the things that were not water-soluble or were covalent compounds. So this is a lot, though, right? This is kind of a lot to write. So then we have the net ionic equation. Let's talk about that. The net ionic equation, so net as in like, well, you know what net means. I don't know how to really describe it. The net means like overall, right? The overall ionic equation. Overall, what is happening? It's the shortest way to write some reactions, and it expresses really what happened, what's really reacting is the idea. But to solve this, you do the same sorts of things that you do for the ionic equation, but then at the very end, what you do, this is the important part, is any ions on both sides of the equation get canceled out. So here's that one of the ones that we did on that previous slide, right? The sodium bromide with the KOH, mixed water, and KBr. But what I'm going to do is I'm going to cross off the things that are on both sides here, right? So I have a bromide on the left-hand side, and I have bromide on the right-hand side. So those are going. I have K plus on the left-hand side, and I have K plus on the right-hand side. So those are both going. Now I do not see just an H plus on the right. I don't see H plus written, so I leave that. I don't see OH minus written on the right-hand side, so I leave that. I see water on the right-hand side. I don't see water on the left-hand side, so I don't cancel those out. I don't cancel those out at all. So that means my net ionic equation here is an H plus dissolved in water, a hydroxide also dissolved in water, turning into water. Just more water. So this would be my net ionic equation, right? So I expanded everything out, so I had all of the ions, and then I just checked to see what ions were there and cut them all, and then I just canceled them out, right? Because nothing really happened, right? What we're saying here is that, yeah, you started with bromide, but you also ended with bromide. So bromide didn't really do anything. It didn't change. It didn't help anything. It didn't hurt anything. It didn't make anything. So why even talk about it? So we just don't. Same thing with the potassium. You had a potassium ion on the left. You had a potassium ion on the right. No change there. It didn't change. It didn't add anything. It didn't do anything. So why talk about it? Let's not talk about it. So what we see that really happened here was that an H plus combined with an OH minus to make water. That's what really happened. That's what really the reaction was. Those are the two things that did it. Everything else is just a spectator ion. And let me put those terms here. These are spectator ions. The ones that you can cross out like that are spectator ions, right? They don't do anything. They don't react. Really, they're just there to balance out charges. And spectator ions are an important vocabulary word for you to know. So again, they're just the ions that you cancel out in that net ionic equation. They're ions that don't do anything. They don't react. They're just there floating around in the water, not doing anything. They're spectators. They're just watching the reaction occur, but they're not part of the reaction. Let's do another one of these net ionic equations, but for this one, so we have to like break everything up. I'll do this kind of quickly because I already broke this up on previous slides. But it has, at first, I need to take my complete reaction, or my complete equation, my molecular equation, and turn it into an ionic one. So I have Na plus and Cl minus and silver plus and nitrate minus goes to Na plus nitrate minus, right? Sorry, this is so long. And then silver chloride, running out of space, solid, silver chloride. But you do the same thing. You find the things that are overlapping, or the things that are in on either side, the things that are redundant. So like, do I have sodium on both sides? Yes, I do. I have one sodium here and I have one sodium here. That means I can cancel them both out. Do I have chlorides on both sides? I don't, right? I have Cl minus, an aqueous Cl minus ion here. But while I do have chlorine here, it's not Cl minus, it's attached to the silver. It's solid. It's this solid silver thing. So I can't cancel out my chlorides because I don't see a Cl minus aqueous here. I don't see a Cl minus Aq anywhere over here. So I can't cancel that out. Same thing for the silver plus ion. I don't see any silver plus ion here, right? I didn't break this up because I knew that it was insoluble. It's solid. I know it's insoluble. So I can't cancel that silver out with this silver because this is silver plus and this is silver in a compound stuck with the chloride. And then lastly, nitrate, NO3 minus, aqueous. I do see that. I do see I have one of those. So I'm able to take that nitrate and cancel it out with that nitrate. So that means now that my net ionic equation would be Cl minus plus silver minus makes silver chloride solid. That would be the net ionic equation. So again, in this case, it looked like my spectator ions are the sodium and the nitrate. Right, where the Na plus and the NO3 minus. So again, this would be the net ionic equation for that reaction. So again, in order to get this to balance, or sorry, let me say this again. In order to get the net ionic equation, you have to go through the ionic equation. In order to do the ionic equation, you need to be able to identify the water-soluble ionic compounds and the strong acids is the idea. So let's take a look at one example that I want you to do. So let's say we have this example, and I say the reaction between lead-2 nitrate and sodium bromide forms lead-2 bromide and sodium nitrate. I want you to write the molecular, the ionic, and the net ionic equation for this reaction. Okay, make sure it's all balanced, everything. So pause here, write the molecular, ionic, and net ionic equation. Okay, so let's take a look at this. So I'm going to start with my molecular because that's just how we would normally talk about these reactions, right? So I see lead-2 nitrate, so that must be this, plus sodium bromide. And let me put in the states too, although it's just more writing, but still. I know that's aqueous, that's dissolved. I've got sodium bromide and ABr. That's aqueous. That apparently turns into lead-2 bromide, PbBr2. I know that's solid because I know it's not soluble based on the solubility rules. And sodium nitrate, which should be soluble. All right, so that would be my complete reaction. I'm noticing, though, right off the bat that this is not balanced. So I need to add a 2 here, and I need to add a 2 here. Let me make this look a little prettier. So plus 2 NaBr AQ. So that would be my molecular reaction. Okay, check. Now, if I want to turn that into the ionic, right, if I want to turn that into the ionic equation, now I need to bust up everything that's water soluble. So that means busting up my lead nitrate. So that means now I've got a fuzzy pen. I've got a lead-2 ion that I'm starting with. I have 2. We haven't seen in stoichiometry, we haven't seen any of these coefficients before, but now I have 2 nitrate ions, right? Because this says right here that in one lead nitrate, I have 2 nitrates. So I need to say that there's 2 nitrates. And I have just one lead here, so I just drew 1 lead. So that 2, it's kind of weird that it was a subscript and now it's just a regular number, a coefficient. But now, because we're talking about how many ions there are, lead-2 nitrate is 1 lead-2 ion and 2 nitrate ions. So that's what we're saying here, 1 lead, 2 nitrates. And then I keep going here. It looks like I have 2 Na pluses, right, because I have 2 sodium bromides according to that balanced equation. And that is going to turn into, and I'm just going to give myself more space. I know I'm already going to run out here. Lead-2 bromide, but that's a solid, so I don't break that up. And 2 more sodiums, Na pluses, and 2 more nitrates. Right, so I just had to go on to that next line there. So reactants are up top, products on the bottom. So that would be my ionic equation. Done, right? There's my ionic equation. Now, if I want to turn this into the net ionic equation, I just need to cancel out those spectator ions. I need to cancel out those things that are on both sides. So is lead-2 on both sides? I don't see a lead-2 ion down here, so I'm not going to cancel that out. Is nitrate ions on the right-hand side? Yes, I do see nitrate ions, so I can cancel those out. So these 2 nitrate ions can cancel out with these 2 nitrate ions. 2 sodiums, yes, I see 2 sodium ions. Those can cancel out with these 2 sodium ions. I don't see any bromide ions, I just see PbR2. So that's it. So that means my net ionic equation then is Pb plus 2 plus 2 Br minuses turn into 1 PbR2. Right, and that would be the net ionic equation. So again, this is how we would talk about the reaction, right? That complete equation. The net ionic equation kind of describes what all the ions are in solution and what they're doing. And then the last one is really what reacted, right? So this was an example of, hopefully you recognize it as a precipitation reaction. This is a precipitation reaction where you mix two soluble things, they come together to form a solid. This would precipitate out, this lead compound would precipitate out. So really all that mattered was that I had lead combining with something that was not water soluble, an ion that doesn't help make it water soluble, like nitrate or acetate, and then it turned into a solid thing, right? That's a precipitation reaction. So that's how you want to approach these. Definitely practice them. They're kind of a lot of work to write out, but you need to remember which are your 6 strong acids and enough of those solubility rules so you can predict whether or not something's going to break up into ions or not. So practice, practice, practice. Let me know if you have questions. Good luck.